So chapter 23 has transition metals and their compounds in it. We're not going to do all of chapter 23. There's certain things I'll mention that we're not going to worry about having to learn because they are beyond what is absolutely important and essential. There's stuff that's interesting, but I'll mention what it is that's more than we need. So transition metals. The D subshells are being filled in transition metals. So we're talking about elements like iron, molybdenum, platinum, copper, tungsten, the metals in the middle, the D block. If you're filling the orbitals, you're filling D orbitals. However, S electrons are lost first when you form a cation, right? If you're talking about, say, iron is argon, 4s2, 3d6. When you form an iron ion, you remove the 4s2 first. So your ferrous ion is argon 3d6. The ferric ion is argon 3d5. You lose the s's. So because you lose the s's first, you end up with a lot of transition metal ions that have partially filled D subshells. D3, D6, D7, whatever. And those partially filled D subshells result in some interesting chemical and physical properties. There's often more than one stable oxidation state, like for iron, +2 or +3 are both stable. For copper, +1 or +2 are both stable. So there are some that +2 or 4, 1 and 3, which is fine. Many of the transition metals have colored compounds. If you're taking the Qual Lab and you did the cation experiments a few weeks ago, remember, nickel is a nice green color in solution. Nickel 2 ion is green. Cobalt ones are more pink. Iron ions are orangey. Lots of nice, pretty colors. Whereas, sodium chloride, calcium chloride, aluminum chloride, they're all clear, colorless solutions, and they're white crystalline solids. The transition metals have colored compounds. Nice blue copper ions and red cobalt ions and green nickel ions, because of the partially filled D subshells in the ions. The wavelengths of light that are associated with some of the electron transitions correspond to visible light when you have the partially filled D subshells. Also, you get interesting magnetic properties. Interesting to whom? Maybe not you, but they are of interest. Remember paramagnetic and diamagnetic? This is part of the chapter that we're not going to deal a lot with. There's a section about details about the bonding in these compounds. We're not going to deal with it a lot. Not that it's extremely difficult, but it's not absolutely essential. There are some other bigger fish to fry in the last few weeks of our course, so that we're not going to worry about it as much. But it operates on the same kind of principle that you might recall in hybrid orbitals, which we don't use very much for transition metals. But recall sp, sp2, sp3 hybridization for like a carbon atom. An isolated carbon atom, 1s2, 2s2, 2p2. There are electrons in s orbitals, in p orbitals. They're spherical, or they're in 90-degree angles to other p orbitals. And carbon doesn't use those orbitals in bonding. Carbon uses sp2 or sp3 hybrid orbitals or something in order to get the observed geometries of 109-degree angles, 120-degree angles, things like that. So bonded atoms often have different kinds of orbitals in use than isolated atoms. The same thing happens for transition metals. The ferrous ion, Fe2+, it's 3D, argon 3d6. And if it was a naked ferrous ion, you'd say, all right, it's 3d6. It would have a pair and 4 singles, according to Hund's rule, back in chapter 8. Okay, fine, that's fine. It should be paramagnetic. However, there are compounds of the ferrous ion that are found to be diamagnetic, which means no unpaired electrons. All electrons are paired. There's no paramagnetism. Because the bonded ferrous ion, it turns out the d orbitals are split. And you get 3 orbitals of one energy, 2 of another, and all 6 electrons might go into the set of 3 orbitals as 3 pairs. And the gap between that and the next kind of orbital is large enough that they don't promote to the next kind of orbital. Other compounds of the ferrous ion might be paramagnetic, where the gap between those orbital sets is small, and so the 6 electrons go in 1, 2, 3, 4, 5, and then the 6th at the other one, and it is paramagnetic. So the bonded atoms may have different electronic properties, different orbitals in use than isolated atoms. given that that happens, you get this very interesting situation with magnetism that's not what you'd expect from Chapter 8, where it's 3d6, so it's got 4 unpaired. We're not going to worry about that as much because we could spend weeks on just that. And we got sort of bigger things to deal with. So the transition metals are commonly found in things called coordination compounds. And the coordination compounds that name comes from the idea that we have coordinate covalent bonds. Coordination compounds involve a transition metal bonded to a molecule or ion that's called a ligand. And down here at the bottom by the bullet points, it's probably the best place to actually start looking at this. It's easier to leave the space above it. But the transition metal acts as a Lewis acid when it reacts with these molecules or ions called ligands. A ligand is some species that acts as a Lewis base. And we recall Lewis acids accept electron pairs, Lewis bases donate them from chapter 18. So looking at this first formula here, there's a couple examples of some coordination compounds. The first formula will elucidate this a little bit. This says CONH3 6 times, all that in brackets, then outside the brackets, Cl3. So there's a lot going on there to unpack. The brackets are confining what's called a complex ion. The complex ion is where everything is covalently bonded within. So everything inside the bracket is covalently bonded. Wait, the cobalt, the metal, is doing covalent bonding? Yes, that's what's going on. The cobalt is forming covalent bonds to the ammonias. The ammonia here has 3 bonds to from nitrogen to hydrogen. Then the nitrogen forms a bond to cobalt, and this happens 6 times over. Same kind of bonding 6 times over. But if we're thinking about how this occurs, the ammonia is a Lewis base because it has a lone pair of electrons. And the cobalt here, the metal ion, accepts that pair of electrons to form a covalent bond. And we call that a coordinate covalent bond. You might recall that term from before. A coordinate covalent bond is that kind of covalent bond that's formed when a Lewis acid and a Lewis base form a new bond. When the Lewis base donates a pair of electrons, we get a coordinate covalent bond. So that's otherwise indistinguishable from every other kind of covalent bond. Once it's formed, it's a pair of electrons shared between 2 nuclei. You can't tell it from a traditional covalent bond, but it's a special kind in its formation called a coordinate covalent bond. So those are covalent bonds within the brackets. The cobalt is covalently bonded to the ammonia molecules. The chloride ions are outside the brackets. So there are 3 Cls, they're outside the brackets. Those are counter ions. So the chlorides here are counter ions, whereas everything inside the brackets is a single complex ion. And, what they say it's a complex ion, it doesn't literally have to mean that it's really complicated, but complex meaning it contains a transition metal and ligands. By definition, that's a complex ion. So there are 3 chloride counterions there. So what's the charge on the cobalt have to be? If there are 3 Cl minuses and there are 6 neutral ammonias, then the cobalt must be +3, right? Cobalt must be +3. Each chlorine is -3. The ammonias are neutral. So more accurately, I'm going to tweak this a little bit. The cobalt here, where I drew that, I'm going to write 3+, because literally it was a 3+ cobalt ion forming that bond. So it's not just CO neutral, it's CO3+ that formed the covalent bond there. So the first compound has a complex ion that's a cation. It's soluble. That compound is soluble. If you dissolve it in water, it releases chloride ions just like a sodium chloride would, or an aluminum chloride solution would have. And those chloride ions are free to react. If there were silver ions in solution, they'd precipitate with the chlorides. But if you dissolve that compound in water, what you don't get is aqueous ammonia. The ammonias are covalently bonded to the cobalt. There are no free ammonia molecules to release into solution. So they're all bonded to the cobalts there. So that bracket contains your complex ion. The next formula there has a complex ion that's an anion. I know it's an anion because here I have 4 K plus counterions. They balance the charge of the anion. The anion must be a 4 minus overall, right? Everything inside the bracket totals as a group 4 minus. Now, do you recognize Cn? Back in chapter 2, there's a list of polyatomic ions. Cn is on there. It's Cn minus, the cyanide ion. Given that it's Cn minus, and there's 6 of them, we could figure out what the oxidation number, what the charge for the iron is, right? If there's 4 pluses, 4 potassiums that are plus, and 6 Cn minuses, we need 2 more pluses, right? The iron must be plus 2. And the iron 2 ion is covalently bonded to all 6 cyanide ions. The potassiums are there to balance the charge, but that complex ion that's an anion contains a ferrous ion, Fe2+, and 6 cyanide ions covalently bonded to it. So this is a different kind of bonding than we're used to, right? We are not used to ions covalently bonding to other things that are neutral or opposite in charge. You know, I mean, ions aren't usually form covalent bonds like this, but here they do. It's a different kind of bonding, but it's good to be aware of. So that's a coordination compound that has a complex ion that's an anion. One thing we're not going to do in the chapter, it's in the chapter, but we're not going to do it, is the naming of these compounds. Naming is, it's not that, you could do it. It's not so hard that you can't possibly do it. It's tedious, it's extra stuff. We're not going to have to worry about it right now. The naming of this, you have to say how many of each ligand there are. You have to indicate the charge on the metal ion, if there is a possible different charge. So the anion here would be, there are 6 cyanide ions, and there's an iron 2 ion. And the iron, if it's an iron in an anion, then they use the Latin part of the Latin version of the name for iron. So this would be the hexacyanoferrate 2 ion. We don't want to get into dealing with that. It's more trouble than it's worth. But hexacyano means 6 cyanide ions. Ferrate 2 means that the whole thing is an anion. The iron is a plus 2. And so the full name of this compound would be potassium hexacyanoferrate 2. Oh my God. And it's got Roman numerals. It's more than we need. So unless there's popular demand, we're going to skip the naming. Don't want it. Okay? Because it seriously gets out of control. We'll see another example in a little bit where the naming, that's only got one kind of ligand. If there's like 4 or 5 different ligands, it really gets crazy. Which order do you put the ligands in and so forth? It's wild. The last one here, this example has 4 ligands, 2 ammonia molecules, 2 chloride ions, and they happen to balance the charge of the metal. So there is no counterion needed. This is a neutral coordination compound all to itself. The platinum is a plus 2. There are 2 chloride ions. There are 2 neutral ammonias for ligands, and so they don't put brackets. Brackets around a complex ion. Convention is not to write brackets around a neutral coordination compound like this, although it could have been a good convention. They don't do it. So that's got 4 ligands, 2 ammonias, 2 chloride ions. The platinum is a plus 2, and that's a neutral coordination compound. So generally, a coordination compound contains a complex ion and counterions. Sometimes it doesn't. And here's a counter example, this platinum compound. Let's see, this would be a diamine dichloroplatinum 2. That would be we have to name it that way. There's a whole hierarchy. You go alphabetically, and you got to say how many there are. It gets really annoying. So, okay, actually it would be bis. It would be bis. Oh, it would be bisamine. That's right. It can't be diamine. Diamine would be a different thing. Oh, lordy. Can't even keep track of it myself. So let's not worry about the naming of them and just worry about the idea that all 3 of those are examples of something that has ligands and a transition metal covalently bonded to each other. Now the ligands, more detail about the ligands. They are the Lewis bases, which means ligands have to have lone pairs. but ligands can deliver more than one lone pair. So about ligands, there are some ligands that are so-called monodentate. A monodentate ligand means that term monodentate literally means one-toothed. One-toothed. The monodentate ligand has one tooth. What it means is it bites onto your metal once. So it could be a neutral molecule, it could be an ion, but it donates a single pair of electrons to the transition metal. And some examples of monodentate ligands include the ammonia molecule. We've seen that above. The chloride ion, water. Let's see, what else is there? The cyanide ion, that's up above. Those are all monodentate ligands. Now, some of those start to bother people when they think about the Lewis structures a little bit. And they say, wait a minute, there's more than one lone pair in some of those Lewis structures. Ammonia, all right, I'll give you that. There's single bonds from nitrogen to hydrogen. I'm not going to bother drawing them. They're not that important. The nitrogen has one lone pair. That's the biggie. The chloride ion. The chlorine has 4 lone pairs. A molecule of water, the oxygen, has 2 lone pairs. The cyanide ion, if you draw the Lewis structure, has a lone pair at either end. How come those are all monodentate? And the reason they're all monodentate is when you form the first bond by donating a pair of electrons at any of those donor atoms, the nitrogen, the chlorine, the oxygen, or for the case of cyanide ion, it could be either, right? The other lone pair, if there is one, is pointing the wrong way. In the water molecule, you got a lone pair, you got a pair, 2 lone pairs on oxygen. And one lone pair makes the bond to the metal. The other lone pair is pointing 109 degrees away, pointing away from the metal. It can't form a bond to the same metal. So water's only ever a monodentate ligand. Cyanide ion, if you form a bond from the carbon to the metal with the lone pair on the nitrogen is pointing the wrong way at the other end. So it can't form a bond to the same metal with both lone pairs on the cyanide ion. So cyanide, water, chloride ion, ammonia, these are monodentate ligands. Even if they have more than one lone pair, only one lone pair can reach at a time. That doesn't mean you can't have more than one lone pair donate from a single species, but it has to be a big enough species to do it. Bidentate, literally that breaks down to 2-toothed. A bidentate ligand has 2 electron pairs to donate, and they have to be on separate atoms that are far enough away from each other. Usually this is the 3rd or 4th atom away. Any closer and it won't reach, any further and it's too unlikely to do it. If you imagine if I had a donor atom somewhere and then 7 atoms away in a chain, there's another donor atom, what are the chances of that molecule actually reaching around and doing it? It's got the entropy of that situation is too high. There's too much freedom of motion. And if it's too short a chain, the limiting case being something like a cyanide ion, if it's only on the 2nd atom away, it's too close. So the classic bidentate ligand is ethylene diamine. If you break that name down a little bit, the ETH prefix, that tells you 2 carbons. So ethane is the 2-carbon alkane hydrocarbon, which only has single bonds, C2H6. Ethylene is C2H4. It's a double-bonded molecule. Ethylene diamine is a molecule that has 2 carbons, 4 hydrogens, like ethylene, the small molecule, but with amine groups at either end. Thus, it's a diamine. So remember amines, they are weak bases. They are ammonia-like nitrogens that have a lone pair and then bonds to at least 1 carbon. So there's an amine group at each end. The amine groups at each end can form bonds to the same metal. M for metal is good. Because the donor atom is the 3rd atom away from the other donor atom. If I count away here, it's 1st, 2nd, 3rd adjacent atom. Depends how you count these things. If you're starting numbering with number 1 as your nitrogen, it would be atom number 4, but we'd say it's the 3rd away, whatever. So ethylene diamine, the symbol for that in common use in formulas is to abbreviate it EN, lowercase en, is fine to use in formulas, or you can write NH2, CH2, CH2, NH2, but it's a lot easier to write EN, lowercase en. It is one of the things, if you're writing in chemistry, writing a manuscript for an American Chemical Society journal, there's a whole style book of how things are supposed to be done and abbreviated and symbols and all these things. And EN is one of the abbreviations that does not require any explanation. Anyone reading a journal from any of the American Chemical Society publications is supposed to know EN is ethylene diamine. You do not have to explain that to your reader, that EN stands for that. This is one of the most common bidentate ligands. So you can put EN in a formula and everyone knows what it is. Or if they don't know, they should have known before they started reading that journal. So that's a bidentate ligand. The lone pair is 3 atoms away. That ligand can form one bond, reach around, form another bond. This molecule, this is tetramethyl ethylene diamine. Names of these ligands are outrageous, right? I mean, all the substituting going on. The only difference here looks very similar, same backbone, right? The difference is we've replaced the hydrogens on the amine group with methyl groups. Methyl is CH3. Methyl is a 1-carbon group. So it's tetramethyl, so 4 methyl groups, 2 on each nitrogen. And so we substituted all the amine hydrogens with methyls. And so this is tetramethyl ethylene diamine. It starts as ethylene diamine, the first molecule, and we add methyls. Again, this is a bidentate ligand. We can form 2 bonds to the same metal with this ligand. The inorganic chemists who use this ligand a lot apparently do a lot of lab work all day with this ligand. Then they go out and get their beverage of choice from the local establishment and sit there and start talking about making their compound. I made my compound with tomato. Do you use tomato? No, I don't use tomato. I just use EN and everything. And tomato is simply the abbreviation for tetramethyl ethylene diamine. And it's a cutesy thing to talk about making your compound with tomato. I don't like tomato on my sandwiches, but tomato in my coordination compounds is okay. I had a waitress get really mad, actually, one time. I was using the slice of tomato that I didn't want from a sandwich as a coaster. They didn't like that. And it was in a bar where there's beer all over the table and everything anyway. It didn't really matter, whatever. So that's a bidentate ligand. They're very similar, right? The key thing is the 2 donor atoms. The rest of it is kind of, molecular level shrubbery. The oxalate ion is bidentate, so you can see the pattern here. It's not important to memorize all these. What's important is to see the pattern. The oxalate ion has 2 lone pairs that can be donated to the same metal. The oxalate ion is the conjugate base of oxalic acid. It's a diprotic acid, so you got to lose 2 hydrogens. But the oxalate ion is C2O4, 2-. It's a bidentate ligand that works very well. Again, it's the 3rd adjacent atom. Has a lone pair from the first donor atom. The other 2 are good bidentate ligands you can teach your baby. ACAC and BIPI. These are nice abbreviations there. I did this to my nephew when he was like 2. It was great. Like ACAC, you like BIPI and everything. He's named after me. Hopefully the only thing he gets from me is the name and not crazy stuff like this. ACAC is short for acetylacetonate ion. No wonder we say ACAC. And the other one, BIPI, is short for 2,2'-bipyridine. This is one of these crazy names that has numbers and punctuation as part of the name. So BIPI is a lot easier than going through all that. So no wonder we say ACAC and BIPI. You can teach your kid, teach your parrot to say these names, and it's very entertaining. ACAC has donor atoms that are actually a little further away, right? This is on the 4th adjacent atom from one donor atom to the next. If you count first, second, third, 4th adjacent. So it's a little longer reach, not exactly the same geometry, but still reach is okay. BIPI, it's the 3rd adjacent once again. Here's a lone pair, and here's a lone pair. And except for the details, that's a lot like ethylene diamine, right? That's a lot like the first bidentate ligand we looked at. Nitrogen, lone pair, 3 atoms away, another nitrogen with a lone pair. Just like EN, just like tomato. Very similar, actually, with the BIPI. The 2,2' comes from the fact that the 2 rings are joined like that, and you start counting at where they're joined, just for your information, so you understand why the numbers have even come along. So carbon number 1 is where they're joined. And so there's a nitrogen at position on the ring, number 2. If we count around the ring, that's 1. There's a nitrogen at number 2. On the other ring, it's also on number 2, where the nitrogen is found. And so it's 2, 2 prime. One ring is the 2, the other is given a prime. Nitrogen could be on position number 3, right? I mean, it wouldn't be a very good ligand anymore if we wanted it to be bidentate, but you could have certainly had nitrogens at, you can have 3, 3 prime, or 2, 3 prime, or something, right? You can have the nitrogens in different positions. So this is 2, 2 prime bipyridine, which is a good bidentate ligand. 4, 4 prime would not be, right? What if it were 4, 4 prime bipyridine? The nitrogens would be here and here instead of where they are. That would not be a good bidentate ligand, right? they would be too far from each other and in the wrong direction. So 2, 2 prime is a good ligand. So that's where the numbers come in anyway. A lot of times there's numbering found in names like that because you've got to give positions on a ring or positions on a molecule somehow. So the common thing to observe about all those is donor atom with a lone pair, and then 3 or 4 atoms away, another donor atom with a lone pair. And that's common to all of those. I posted the old exam for practice yesterday. So there's old exam questions about this kind of thing. The one where, there's already some up there, but this is the one that's like, try to save it for, give yourself an hour and a quarter, pretend it's the test, take it and see, and the answers are written at the end. And you'll see, if there's a question about a compound that uses any of these ligands, it tells you about it. It'll, like, even if it's EN. EN is familiar, hopefully, by the end of doing stuff like this, but if there's EN in a formula, it would say, note, EN is ethylene diamine, comma, a neutral bidentate ligand. It's up to you to know what neutral bidentate ligand means, right? Neutral means it has no charge. Bidentate means it connects twice. And that is important to doing the problem. We'll get back to that shortly, where that comes in. But you don't have to memorize your BIPI and your ACAC and your EN and everything. No one's going to ask you to draw them. But if you're familiar with them, it saves time on the test. If you see a BIPI or an ACAC or a EN, it's not new to you. Whereas people who never come to class, it'll be the first time they ever see it on the test. They'll be so confused. And then, more is the pity. After bidentate, there are tridentate and tetradentate. There are molecules and ions that donate 3 or 4 pairs. This is an extreme example of a polydentate ligand. This is a hexadentate ligand. This is a single ligand that donates 6 pairs of electrons to the transition metal. It wraps right around the transition metal, the single species here. This is ethylene diamine tetraacetate ion. The names on these things, outrageous, right? Ethylene diamine is where it starts. We recognize that? Recognize this part of the molecule here? That's EN, right? That's nitrogen, carbon, carbon, nitrogen, lone pairs at the ends. And then attached to the nitrogens are 4 acetate ion groups. Remember, acetic acid is CH3COOH. The acetate ion would be CH3COO minus. And that's what we got here. We have CH2COO minus. CH2 because we need a place to form a bond. So this is like you attached 4 acetate ions to an EN molecule. So this is kind of like messing around with the EN to make tomato, right? Instead of attaching methyls, we attach acetate ion groups. So we have 6 donor atoms. You've got a pair there, a pair there, there a pair, there a pair, everywhere a pair, and 6 donor atoms. This is hard to draw in any way that looks three-dimensional because it's so big. But what you need to imagine is a single transition metal ion, and this ligand wraps around it completely. It forms a bond above and below. It comes in from the left and the right and the front and the back. Forms 6 bonds. It's hard to draw on a flat sheet of paper how that looks. But this is EDTA. You don't hear as much about EDTA as you used to. With foods and stuff, there used to be commercials that would say, oh, our product now doesn't have any EDTA in it. EDTA is common as a preservative. It's found in everything from beer to mayonnaise and everything in between to slow the spoiling process. But this is actually an anion. If you had a low enough pH, if you added hydrogen ions, you would have protons, hydrogens, attached to all of the 4 oxygens at the ends there. And you could write the formula. You could write like H4 EDTA. So the EDTA is the symbol for this conjugate base 4 times over of that weak acid. But that's a hexadentate ligand. Sometimes this is used if someone's been poisoned by a certain transition metal. This can scavenge and cage the ions up and carry them off so that they can't form any more bonds because it surrounds it with 6 bonds. So the ligands provide lone pairs. They are the Lewis bases. The transition metals are the Lewis acids. They are the acceptors of the pairs of electrons. And about the metals, the one thing that we need to be aware of on our metal is its coordination number, so-called coordination number. See if I can make this a little smaller. Oh, there it is. Thought I had tapped in the box, but let's try that. Little small. There we go. Okay, smaller, but not too much smaller. Coordination number tells you how many bonds are there between the transition metal and the ligands. So number of atom-to-atom connections, the number of bonds between the transition metal and the ligands. It's not necessarily the number of ligands. Got to be careful on this. Sometimes people way oversimplify it and say, oh, it's the number of ligands. Not necessarily, especially not on the test, because there's always a question that's asked in a way that if you think that's what a coordination number is, you'll blow it. Coordination number tells you how many bonds between metal and ligands. And the coordination number depends on a number of different things: what the transition metal is, the size, the oxidation number, which it would, is the same thing as the charge. So all those things influence what the coordination number would be. Iron tends to have a coordination number of 6, sometimes 4. Silver, on the other hand, is usually a coordination number of 2, and there's others in between. So depends on what it is. Now, here's a formula here. We'd like to know a couple of things about the iron. I'd like to know, for that coordination compound, what's the coordination number of the iron, and what is the oxidation number of the iron? So the coordination number and the oxidation number. So, how are you going to get the coordination number? The Cl2, by the way, in there, it's not molecular chlorine. Sometimes people see Cl2 and they think maybe it's Cl2, the element. Not so. It's 2 chloride ions. Okay, Cl2 with lone pair, with more than one lone pair on each chlorine, theoretically could be a ligand. It's never a ligand. It doesn't do that. But that's 2 chloride ions. So how many is the coordination number of the iron here? How are we ever going to figure that out? Why is chlorine written twice? Why do I have Cl2 close bracket Cl? Why not just write Cl3? What's the difference between the chlorides? The ones inside the brackets are ligands. The one outside the brackets is a counterion. If I had a mole of this compound in solution and I added excess silver nitrate, how many moles of AgCl do I get as a solid? Just 1. I got 1 mole of free chloride ion. The rest of the chloride ions are ligands. They're covalently bonded to the iron. They do not dissociate into solution. So if I dissolved a mole of this in water and I added excess silver nitrate, 1 mole of chloride ion would precipitate with the silver. The other 2 moles of chloride ion are covalently bonded. So how many ligands are there? We got 2 chloride ion ligands and 2 En ligands. Total of 4 ligands. The coordination number must be 4, right? Right? Wrong. Wrong? Wrong. Feel like it's the McLaughlin group, or at least the Saturday Night Live version of the McLaughlin group. Wrong. Yeah, there's 4 ligands, but the ENs are bidentate, right? If you imagine how this would look, possibly, the iron here is bonded to 2 nitrogens from the En. It's common if you're cartooning a thing like this to just draw a curved line from one nitrogen to the other. The backbone of the ethylene diamine ligand, to the inorganic chemists that care mostly about the central metal atom, it's not important to draw all of the specifics of the ligand unless it's an important thing. It could be important, but in this case, just for quickly adding this up, it's not the biggest deal. All right, so that's a bidentate ligand. It forms 2 bonds. Same with the other En. There's a second En, and it forms 2 bonds as well. And then I got 2 chloride ion ligands as well. So how many bonds is that drawn to the iron? 6. There's 2 bidentate. Each of them makes 2 bonds. There's 2 monodentate. Each of them makes 1 for a total of 6. So the coordination number is 6. So not 4 and not 5. Sometimes people will say there's 2 ENs and 3 chlorines. That's 5. No, it's not that either. Okay. Or 7. If you're writing this as a multiple choice question, it's great. There's 4 is a wrong answer, you get one way, and 5 is a wrong answer, you get another way. 7, people say, oh, ethylene, diamine, there's 2 bonds for each, and then there's 3 chlorines bonded for a total of 7. That's wrong as well. Your heart's in the right place, but you're not supposed to count this outside chlorine. It's not a ligand, so 7's wrong. 6. So it's always on the exam. If you look at that old exam I mentioned, or any of the other older exams that are already up there on the web, there's always a question like this. You change the metal, you change the ligands, it's a whole new question. But it's the same principle every time. It's not that I'm trying to be lazy on this, it's just that, the question always works. So the people who don't come to class, more is the pity, will have no idea what to do. So the coordination number is 6. By the way, if you're wondering, how do we know that the chlorines are opposite each other like that? How do we know they're not next to each other somehow? Actually, right now, we don't know. This was just a quick thing to count the bonds. It wasn't actually necessarily doing the geometry. At the moment, we don't actually know if the chlorines would be opposite each other, or maybe they are next to each other somehow. That we'll have to deal with in due course. But right now, we're just counting the bonds. It's definitely 6. How about the oxidation number? How are we going to get that? It's a little easier in a way. For that, it doesn't matter what's a ligand, what's a counterion, just add up all of the charges. So I have 3 chlorides at -1 apiece. They total -3. 2 of them are ligands, one's a counterion, but they're each -1. So there's 3 of them total, for a total of -3. And the ethylene diamines are neutral. So that's a total of -3. Therefore, the iron must be +3. So that's a classic exam question to ask. Here's a formula of some coordination compound, and what's the coordination number and the oxidation number of the metal in it? And if this were on the exam with this one, it would say near the question, note, En represents ethylene diamine, a neutral bidentate ligand. And the fact that it's neutral is germane to the oxidation number. And the fact that it's bidentate is germane to the coordination number. So you need to know both things to do both parts of the question. The fact that it's bidentate doesn't affect the oxidation number. And the fact that it's neutral doesn't affect the coordination number. As we saw up above here, there are some bidentate ligands that are charged, like ACAC or oxalate ion, and there are some that are neutral, like tomato or En or BIPI. God, the names are great, right? When you abbreviate the names, people would think it was crazy talk, right? They'd walk in on these inorganic chemists talking, I'm mean, BIPI and tomato and ACAC, BIPI, tomato, ACAC. Oh, what? I don't know if I've walked into chem lab or preschool or what it is, but oh well. So the charge and the dentate number, monodentate, bidentate, etc., they factor into different things. So how are we doing? How are we doing so far? Feel okay so far? You know what to look for. Okay, don't panic when you see some. We could even have some random new ligand you've never heard of, right? If we wanted to spice it up a little bit, have some kooky new ligand that you've never heard of, and it would say on the exam it's bidentate, it has a charge of -1 or something, and you'd know what to do. So we don't have to stick to ACAC, BIPI, tomato, and En. We can use whatever we want. It's just that they have such fun names. Vamping for questions. Okay. Without objection, we move on to the shapes. So let's get into the shapes a little bit. Like we mentioned above here, it looks like the iron has 6 bonds. It has a coordination number of 6. Those 6 bonds in space will be arranged a certain way. These are the 4 most common geometries for coordination compounds. This is from table 23.5, or 23.5. I guess it's not really it's not a quantity, it's just a number. 23.5. The most common coordination numbers by far are 2, 4, and 6. The coordination numbers are sometimes anything from 1 up to 9. More than 9 is not often seen. Up to 9 is sometimes found if you have a very large metal ion and really small ligands. You can fit 9 of them around. However, if you have a tiny metal ion and huge ligands, you're going to be more limited in your coordination number possibilities, fitting the things around there. But 2, 4, 6 are by far the most common. For coordination number of 2, linear is what's observed virtually all the time. 2 bonds, 180 degrees from each other. These are familiar geometries, things like linear and tetrahedral, right? We remember those from chapter 10. However, the shapes are not the same. I should say the shapes are not what they are for the same reason as they were in chapter 10. Okay, in chapter 10, something was linear because the central atom had 2 bonds and no lone pairs, or possibly 2 bonds and 3 lone pairs. In VSEPR, that's how it works. In coordination compounds, it's different. We don't worry about counting lone pairs and things like that. Counting the valence electron stuff is all different for transition metals. So we're not going to worry about draw the Lewis structure, count the lone pairs, derive the shape. It's different things that influence the shapes here. But the geometry is the same. So linear now is the same linear as you learned in chapter 10. For coordination number of 4, there are 2 different geometries observed. Square planar and tetrahedral. And you've seen them both before in chapter 10. If something were square planar back then, it was because it has 4 bonds and 2 lone pairs. Here, it's not about that. So we're not going to worry about bonds and lone pairs. It's about something else. Tetrahedral, 109 degree angles. Square planar, 90 degree angles between the bonds. What does play into the decision, is something going to be square planar or tetrahedral, is stuff like the electron configuration of the metal. Square planar is observed, for example, in complexes where the transition metal has an electron configuration that's D8. Platinum 2 compounds are D8. If you do the electron configuration of platinum 2 ion, neutral platinum would be, let's see, it's number 78. It would be xenon 6s2, 4f14, 5d8. Then you lose 2 to make platinum 2. So you lose the 6s2, right? You don't remove from anywhere else. You remove from 6s2. So you take those away. So platinum 2 is xenon 4f14, 5d8. Being d8 makes it be square planar. For whatever reason, things that are d8 are square planar. On the other hand, things that are d10 are always tetrahedral. For example, zinc ion. Zinc ion is argon 3d10. You lose the 4s2 from a neutral zinc, you get 3d10. So d10 is always tetrahedral. d8 is always square planar. And there are other trends we observe. Now, then people say, well, what about d7? What about d3? There's sometimes other reasons for the things to occur. And sometimes there's a little variety, but there's nothing we ever see where a particular transition metal with the same charge is tetrahedral half the time and square planar the other half of the time with a coordination number of 4. Usually it goes one way or the other. And for these particular electron configurations, this is what's observed. I mean, there's other ones as well, of course. Not everything. You can have D0 through D10, right? But this is what's observed for those particular ones. So there's reasons in play. It doesn't have to do with how many bonds, how many lone pairs. It does pertain to the electronics. 6 electron, a coordination number of 6. 6 bonds, octahedral. Seen that geometry before as well. That's where the bonds would be, if you like, on the x, y, and z axes of a 3-dimensional coordinate system. So we'd have 90-degree angles. So we have bonds on the x and the y and the z, positive and negative. Those are the most common geometries. And there are others. If you have a coordination number of 3, you can have trigonal planar. Coordination numbers of 5, 7, 8, 9. They're observed. They exist. But they're much more rare. So these are the most common ones to see. Square planar versus tetrahedral does make a difference. There's certain things, as we'll see shortly here, there's going to be a couple of things I want you to build, if it helps you see it, where one of them is square planar, one of them is tetrahedral, and then on Thursday, we can go back to a couple of things and ask, if this were square planar instead of tetrahedral, would we have seen the same thing? And it turns out probably not. So those are the most common geometries. Now the fun begins. Wait, the fun's only beginning now? I thought the fun around here never stops, right? What do you mean the fun begins now? Well, it gets more fun than it already was, with something called isomerism, or isomerism. If you like to put the accent on a different syllable, you can say it that way. Isomerism is the phenomenon that occurs when you have isomers. And isomers are two or more molecules or ions that have the same number and kinds of atoms but arranged differently. So that means they have the same formula because they have the same number of all the different kinds of atoms that are found in them. But they have different properties somehow. The members of a group of isomers are going to have different properties in some way. They might have different physical properties, or different chemical properties, or different physical and chemical properties. And this bothers people if they break it down too much. They say, wait a minute, are you saying that there are some isomer pairs out there where they have the same physical yet different chemical properties? That doesn't seem possible. To have different chemical properties, they must be totally different things. But it does occur. It's not very common, but it turns out we're surrounded by it in our world, actually. But there is a particular situation where a pair of isomers, the two different molecules, can have all the same physical properties, density, color, boiling point, etc., yet have different chemical properties in certain situations, which seems counterintuitive, but we'll see what it is by the end of the day. Isomers don't exist for every possible situation. Not every coordination compound has isomers that could. As we'll see, there might be a situation where you have a structure. You say, oh, if we did this, we could have an isomer. But experimentally, it doesn't occur. And the reason for that is often because of things where bonds are formed. If we have an octahedral geometry, for example, or a square planar geometry, where we have a bond on one side, we have a bond over to one side, the orbitals on the central atom that are involved in forming that bond may have lobes that are on the other side. And that's going to affect what kind of bonding you can form on the other side. And so what's bonded on the right is going to be influenced by what's bonded on the left. And some things might not be able to bond on the right that would make the isomer. So there are certain reasons that isomers aren't observed every time they possibly could be. It makes life a little easier, in a way, because we don't see isomers that could exist. But that's fine. So I know I'm not usually very official and outliney and everything in notes, but there is a hierarchy and a structure to the kinds of isomers. So I went along with a very formal outliney kind of structure here, that there's Roman numeral 1 and then capital A and B under Roman numeral 1, etc., to organize it. The first category in the classification of isomers is structural isomers. Structural, sometimes called constitutional isomers. Constitutional, not because it has anything to do with politics or anything. Structural isomers contain the same atoms but with different bonds. So they are constituted differently. The members of a pair of constitutional or structural isomers are constituted differently. They have different bonding in them. The first kind of structural isomers that we talk about are coordination isomers. There are four kinds of isomerism total. 2 in Roman numeral 1 and 2 in Roman numeral number 2. And I have them arranged from the most in your face when you write the formulas to the most subtle. And we'll get to the most subtle one at the end today, and then we'll reconsider it next time too. So first, under structural isomers, is something called coordination isomers. Coordination isomers involve a difference in the composition of the complex ion. What's usually involved in coordination isomers is a ligand and a counterion trade places. So looking at the first formula here in this example, we have Cr and H3 5 times, OSO3, close bracket. Okay, so everything inside the bracket is part of the complex ion. Outside the bracket, we have bromide ion. So Bromide ion is a ligand. What's this species here? OSO3. Turns out that is a sulfate ion. Oh, God, I can't believe I wrote ligand. I cannot believe. I said counterion and wrote ligand. Are you serious? Oh, well, I got it right twice earlier. I get some slack, right? Can't believe I said counterion, wrote ligand, can't keep things straight. Oh, well. Bromide's a counterion. The sulfate ion here is a ligand. We're going to switch them, but not just yet. Now, the sulfate ion is a ligand, but it's written oddly, right? The OSO3, maybe that was jarring somehow. Why is it written OSO3? There's a reason. Convention when you're writing these formulas is that you write the donor atom, the one that's donating a lone pair of electrons, closest to the metal in the formula that's forming the bond to. So closest to the chromium, we should write the donor atom. And the lone pairs in the sulfate ion are found on the oxygens. The sulfur does not have any lone pairs. Knowing that, it could be argued that it wouldn't be bonded through the sulfur. Everyone knows it's bonded through the oxygen, so why not write SO4? But that's not how it's done. The convention is to write it with the donor atom first. The only exception I can think of is that often water is written H2O, not OH2. And, that's because hydrogen only forms one bond. It couldn't do it. Water you sometimes see written H2O. It's technically written OH2, though, for this reason, that we write the donor atom first. So the chromium here is bonded to, it's got bonds to 5 ammonias. I'll just write the nitrogens for those. And then here it's bonded to the oxygen, which is bonded to the sulfur, which is bonded to the other oxygens, and the sulfate ion. So the sulfate ion is a ligand. The bromide ion is a counterion. If you dissolve this compound in water, the bromide ions would float away as Br minus Ac. The other compound has the chromium bonded to, again, 5 ammonias, but covalently bonded to a bromide ion. Here, the bromide ion is a ligand, which I wanted to write the first time, which was wrong. Right, wrong. And the sulfate ion here is a counterion now. It's not covalently bonded to chromium anymore in the second compound. So these are totally different compounds, right? One of them has a chromium-bromine covalent bond. The second one does. The first one has a chromium-oxygen covalent bond in it. One of them is an ionic bromide. The first one is a bromide, ionic bromide. If you dissolve it in water, you get bromide ion in solution. It could precipitate it with silver. The second compound, if you dissolve it in solution, is an ionic sulfate. It would release sulfate ion into solution. So they're totally different compounds with different ligands, but they have the same overall formula, right? Each of those has 1 chromium, 5 nitrogens, 15 hydrogens, 1 sulfur, 3 oxygens, and a bromine. Take the whole box of atoms to build that, probably. So lots, but they're all the same. They have the same molar mass, the same formula overall, but different bonding. Different kinds of bonds are found. So this is the most in-your-face kind of a pair of isomers, because the formulas are written completely differently. You switcheroo ligand and a counterion to form the other isomer. So that's easy to notice if you know what you're looking for. If you had one of these exam questions that said, how are these two related, formula and other formula? And A, B, C, D would be the 4 kinds of isomerism, and E would be they are identical. They're not isomers at all. They're the same thing. These are coordination isomers, because what was a ligand in one is a counterion in the other. Linkage isomers are also in the category of structural isomers. Linkage isomers involve when a ligand could bond via more than one atom, different donor atoms. This example here, as we see, the difference between those two formulas is that group that I underlined, which happens to be the nitrite ion, NO2 minus, the nitrite ion. Here is 1 Lewis structure of the nitrite ion. Then there's a resonance structure that has the double bond on the other side. But that's one resonance structure. And we see it has two possible donor atoms, right? It could form a bond through the N or through the O. But not both. It's not a bidentate ligand. Even if it formed a bond through one oxygen and then tried to bond through the other oxygen as well, that's too close. That's only the second atom away. It has to be further than that. So nitrite ion is a monodentate ligand that can bond through N or bond through O. And the first one is bonded through N, right? The first one has a cobalt-nitrogen bond, where then it's bonded to the oxygens. The other one has a cobalt-oxygen bond, where the nitrite ion is bonded by O. Thus, it's written ONO instead of NO2. So it seems nitpicky on the first one. Well, why not write sulfate as SO4? It's bonded through the oxygen. Well, here's where it's important. The only way to tell someone that this is N bonded to cobalt or O bonded to cobalt is to write the ligand the appropriate way. And this is a hat tip to Dr. Burmeister at Delaware, Dr. John Burmeister. He's retiring after 50 years at Delaware. And I took the second semester of chemistry, the class like you're taking, from Dr. Burmeister. And his lab research, especially earlier in his career, was a lot to do with linkage isomerism. And the term that they coined for that was ambidentate ligands. If you're ambidextrous, you can write with either hand or something. If a ligand is ambidentate, it can form a bond with either donor atom. And so ambidentate ligands include things like the nitrite ion. And looks like a small difference, and it's not the hugest difference in the world, but one of those compounds in the solid state, pure compound, one is red, one is orange, because the cobalt-oxygen versus cobalt-nitrogen bond is a different energy bond, corresponds to a different energy of light when it interacts with visible light. So it's a minor difference, but observable and important. And there are other ligands that do this as well. These are a few other ligands. SCN-, the thiocyanate ion, can bond through the S or the N. The cyanide ion, CN-, usually bonds through the carbon, but can bond through the nitrogen. And if it bonded through the nitrogen, how would it be written? In a formula, it would be written NC, right? Instead of CN, it would be written NC. So you can't just write the ligand atoms in whatever order you like. You got to, it reflects how it's bonded. So you actually have to write it accurately. And then the cyanate ion, OCN-. That's one that is ambidentate as well. If it's OCN, it means it's bonded through oxygen. If it's written NCO, it's bonded through nitrogen. And either could occur. It doesn't always happen in every place that it could. There are lots of thiocyanate complexes, SCN-, that you don't see the NCS linkage isomer for. But they do exist. By the way, as an aside, again, naming is not something we're going to have to worry about. But in the example above with the cobalt, the NO2 ligand there, in the naming of that compound, in the name, it would take the name nitro. And so this would be a, this would be a tetraamine chloronitro. You have to alphabetize the ligands, put prefixes for how many, but that's nitro. The ONO in that other compound, for the naming part of that, takes the name nitrito. The ligand is named differently because it's linked through a different atom. Those are different compounds. They have to have different names, and that's how they do it. They actually change how the ligand is named. Told you we don't want to have to worry about getting into the naming. This could be really annoying if we let it. It's not extremely hard. There's stuff to memorize, rules to learn, and it's tedious, and we got more important fish to fry. We got to pick our battles. But they do have unique names. So NO2 is nitro, and ONO is nitrito, and there you have it. So those two types of isomerism, the structural isomerism, are applicable to coordination compounds. The next two kinds of isomerism that we're going to talk about are applicable to not only coordination compounds, but also to organic molecules. And that's why in the syllabus it mentions, while we're doing this stuff in Chapter 23, to also look at section 15.2. That's where the organic chemistry is in chapter 15 at a superficial level. And 15.2 has some information about these two kinds of isomerism that we're going to talk about. It's also in chapter 23. But in the context of organic compounds, it's in section 15.2. So it's worth mentioning because these two kinds of isomerism apply to organic molecules as well as transition metal compounds. So first, let's see. Roman numeral 2, stereoisomers, so new category. The previous category, again, category number 1, was the structural or constitutional isomers, where the bonding is different. In category 2, stereoisomers, we have the same atoms and the same types of bonds everywhere. Every atom has the same type of bonding. It's only the arrangement in space that changes, and this is tougher. This is where, people have to visualize. People have a hard time sometimes visualizing how these things work. Spatial relations, if you've heard that, people talk about, how is your spatial relations thinking and stuff. If you have a hard time visualizing how things are in space, this can be more challenging. So it's useful to have the models. That's why I have the models. There's a couple of things I want to ask people. If you really don't want to, you don't have to, but I'll build this and see what you get. So under the category of stereoisomers, the first category, A, is geometric isomers. Geometric isomers, sometimes called cis-trans isomers or diastereomers. Geometric isomers involve when you have a different arrangement in space of the same types of bonds. For example, this formula that we saw above, the platinum 2 compound. So platinum with 2 ammonia ligands and 2 chloride ion ligands. Being platinum 2, it's going to be square planar. So here's the task. Okay. In the box there, somewhere there should be some atom that can be used as a square planar. In this particular box, there's 2 out of 3 of the colors here. So it may be yellow, it may be this tan color, it could also be the silvery color. This box does not have the 6 holes. We're looking for one of 6 holes, okay? So it could also be this silver color. So it's either yellow, tan, or the silvery. Find one of the 6 holes. And with the 6-holed atom, we're going to make something. You can make something square planar, right? Just leave the top and bottom vacant. But here's what I want you to build. I want to see what people build. This is interesting. It's always interesting to see what happens. Take the bonds and make something so that's square planar. So you got the 4. I know it's small here. So I used the yellow. So put 4 bonds on it. And leave the other 2 blank because we don't need the 5th and 6th positions. And try to build a molecule of PT, NH3 twice, Cl twice. Okay, go ahead and try building that. The usual color convention is nitrogen is blue, chlorine is green. It doesn't really matter as long as you know your own color coding is. So if you want the nitrogens to be red and the chlorines to be black, that doesn't really matter. But whatever it is. But build that. Just whip something together. You don't have to put all the hydrogens on the nitrogens if you don't want to. Okay, you can put hydrogens on the nitrogens, but main thing is, I want to see what people build. Shouldn't take too long. Try building one. I want to see what people build. And so try building. It's always interesting to see what people build. And nobody has to share. There's enough of these for everybody. It's not like earlier, people had to share with people they didn't really like, but that's okay. So, there's enough of these in a smaller class that everybody can do it. So try building one of those. Won't take long. You don't have to do all the bonds on the ammonias if you don't want to. If you want to, you can. But the main thing is the bonds on the platinum. Okay, the platinum is going to be that central atom. Again, the central atom could be tan, it could be silver, or it could be yellow. Different boxes have different 6-hole atoms that are, all identical otherwise. They are all cast in the same mold at the factory with different colors. Okay, so give you just a minute to see what you come up with. Don't want to take too long, because I want to make sure we get through the next category too. Almost there. If you're not, it's okay. But if you're done, hold up what you have. There's more than one right answer. Don't be shy. All right. So we got blue across from blue there. Got blue across from blue. Oh, you got blue next to blue. That's fine too. That's fine too. Okay. Hold that one up. Hold that one up so we can see. That's fine too. Okay, so can you see that? Anyone else got blue 90 degrees from blue? Okay, so there's a lot of ones that have blue across from blue and green across from green. It doesn't matter if it's blue, green, red. It doesn't matter what your color coding is, but identical colors across. Now, you had blue next to blue, which is actually kind of cool. I needed somebody to do that. Okay, so different people, a couple of different geometries there. Now, the one you had, you still got that sort of there? You got the, yeah, so you got, so hold it up good there. I don't know if you can see it. Can you see that the greens are next to each other, the blues next to each other? Now, someone over here has got one that they're, hold that up high there. So, see, now there the greens are across from each other, right? And so you could, if you have one built, you can take apart what you have and reverse a couple, switch them, and get the other. But you have to break bonds, right? Those are different structures. So here's one of them, where the like ligands are across from each other. And the other possibility is to have the like ligands, for example, the ammonias, next to each other. And that would leave these chlorides being next to each other as well. So this is pretty good. It always works out that at least a few people build one and some people build the other. I've never had everybody build the same exact thing, which is good because both structures do exist. The left-hand structure here is the so-called trans isomer because the like ligands are across from each other. Trans means across, like the Transcontinental Railroad, across. The like ligands adjacent here would be called the cis isomer. You only have to have one pair to do cis-trans. Here we have two pairs, but you could have just one pair. If we had two ammonias, a chloride, and a water, for example. The ammonias could be cis or trans, and then the other two would occupy the positions that are left. So you don't have to have two pairs. But this is, here we do. The cis isomer here is used in making a cancer medicine. The trans isomer is slightly poisonous. These are really different compounds. Okay, so they couldn't possibly be more different in their properties. The cis isomer, as we'll talk about on Thursday, is used in some cancer compounds that are sort of classic cancer drugs at this point. Been around for a while. These platinum. There's a guy gave a talk. We're having the awards dinner tonight, actually, for chemistry majors. I'm going to get out of here and go to the Sheraton Suites for the awards banquet for the chemistry majors. And the speaker that comes and does the night lecture a few years ago, he did a lot of the stuff with these platinum compounds. He was joking that the gold standard of cancer therapy is platinum drugs. It should be the platinum standard, but whatever. Now, you see cis-trans with carbon-carbon double bonds as well. Here are two molecules that are C2H2Cl2. And they have the same types of bonding. That is to say, each carbon is bonded to a hydrogen, a chlorine, and the other carbon in both molecules. So they are geometric isomers. The left-hand molecule in this case here is the cis isomer because both chlorines are on the same side of the double bond. The other one is trans because the chlorines are on opposite sides of the double bond. And if you hear people talk about trans fats, now we're cooking, oh, it's great, I can eat the whole bucket of chicken because they're cooking without trans fats. It's healthy now, right? No, it's not. That's overdoing it. But trans fats, this is the trans in trans fats. Long, greasy molecule, hits a double bond, goes across and continues in the trans position. That's trans in trans fats. So trans fats are worse for you than cis fats. But so that's cis, trans with organic chemistry. It's not, where do you see a square planar carbon atom? Never, right? So cis, trans, and organic chemistry is different. It's not square planar stuff or something, it's double bonded. But it's the same idea. Same types of bonds, different arrangement in space. Now the last one, we're going to introduce this today while we have the models. We're not done talking about this kind of isomerism though today. We're going to discuss it on Thursday as well. But the last task on the models here is to introduce enantiomers, also known as optical isomers. So the last task is, if you have a couple of black atoms with 4 holes, those are usually used for carbon, tetrahedral. Here's the task. If you are sitting near somebody and you want to just, if there's each of you has a thing you want to share the labor, you can do it that way. Put 4 bonds in your carbon here, and then put 4 different colors on your tetrahedral carbon. If you have 4 different colors. If not, borrow from someone nearby. So red, blue, green, and black, or you could use another black. Red, blue, green, white. There's orange sometimes, yellow, whatever. Put 4 different colors on your tetrahedral carbon. Then build its mirror image. Won't take long. Won't take too long. There's just enough time to do this because there's more to talk about with this last kind of isomerism. But this is worth doing while we have the models here. Build that and its mirror image. I've already got and you're saying, gee, we're going to run out of time. We're doing perfect on time. We can build this tonight. So here's a larger version example of what we want. Okay, so here's one that's got 4 different colors. And then build the mirror image. So imagine a mirror reflecting. So I built this one. Imagine a mirror here. Okay, so I built its mirror image. So try that if you're sitting with somebody else and each of you builds one, that's fine. So build that and its mirror image. If we talk about this, it's hard to see, but if you see it with a physical item, sometimes it's a little easier to visualize. This is good. We're right on time. Don't worry. We're not done talking about this thing yet. What we're talking about here is something called optical isomers. We'll get to more detail on that on Thursday, but if you've got that one and its mirror image, if you're still building it, if you're almost done, don't worry. We're not gonna get too far, but while you're still building it, here's the question about the 2. Okay, take those 2 and see if they're identical. Can you superimpose them completely on each other? I'll try it with mine here, okay? So to get them to be, okay, so once again, here they are as mirror images, right? If there's a mirror, we're right in the middle here, okay? So if I line up green and red, dang, blue and white don't line up. Maybe I'll line up blue and white. Shucks, now green and red don't line up. Maybe I need to do green and blue. Maybe if I do green and blue, phooey, now red and white don't line up. I'm running out of polite curse words, right? Darn, shucks, phooey, rats. They're never going to line up. These are not identical. Even though they're mirror images, that may be counterintuitive, but they are not identical, even though they're mirror images. And this might be counterintuitive, but there's other examples like your hands. Your hands are non-superimposable mirror images. So are your feet. So are these. They're mirror images. Anytime you have a tetrahedral central atom with 4 different groups attached, you have the existence of enantiomers, which are also called optical isomers. I'll get back to the zinc one on Thursday, but what I want to mention right now is enantiomers are everywhere, or at least the possibility of enantiomers. Proteins are made of things called amino acids, and you might know there are 20 amino acids that go into making proteins. 19 out of the 20 exist in a way that there could be a pair of enantiomers. Those amino acids have a carbon that's bonded to a hydrogen, a carboxylic acid group, and a amine group, thus amino acid, and then R, which represents some other group. And only in the amino acid called glycine. R is hydrogen in glycine, so 2 of the atoms are identical, attached to carbon. That one doesn't have enantiomers. The other 19 of the 20 amino acids found in proteins have R that is not the same as any of the other 3 things on that carbon, which means that carbon, which is tetrahedral because it has 4 bonds, is going to be a place where optical isomerism could occur. Tetrahedral carbon with 4 different groups. Like this, right? So we could have this or its mirror image, and they're different. And that is going to be important for your body. If you take a protein supplement, say you got some bootleg counterfeit protein supplement, and it's made with the other enantiomer, your body won't know what to do with it. It'll literally either make you sick or pass through without doing anything, depends what exactly it's made of. But it won't go into any proteins or anything if it's got the wrong amino acids, even though it's all the right stuff, if it's the mirror image. And that's the thing here about chemical properties. Enantiomers have different chemical properties in environments that contain other enantiomers. So that's where we'll pick up, where we're in the middle of the enantiomers. Fine, sometimes it's good if you get that far. Now people can stew on it for 22 and a half hours and say, wow, that mirror image thing still, we're going to get back to it. We'll get these back out the next time. We still have a little more to talk about on it. But hopefully it helps a little bit to see those and hold them and everything. If you want to get them back out before class the next time, if you get here early and you want to play with one of the model sets any day, they're in the back room. If you come to class early, you want to get one out, just ask. That's fine. Okay, so we're still on this. Don't panic. If you're coming by and you want to bring the box by, that's fine. Otherwise, I'm going to run around, but we'll be fine. So let me know the next time. Okay, next time in class, if you want to get these models back out, we can get them back out.